Hello everyone, I hope you're having a great day today. So in this video, we're going to balance an equation for a redox reaction, oxidation-reduction, taking place in basic solution. So the last video I did, it was acidic solution. You can find the link to that video right down there in the description if you're interested. But this video, we're going to do it in basic solution. So let's get right into it. So the equation is this right here, where we have the NO2 minus, that's the nitrite ion, reacting with elemental aluminum to produce ammonia, NH3, and AlO2 minus, that's the aluminate ion. So the first step, what we're going to do is we're going to assign oxidation states to every atom, every element in this equation. So if you want a more comprehensive lesson on that, there are a couple of links to my Redox Part 1, Redox Part 2 videos. You can find those in the description as well. But for the purpose of this video, we're going to sort of understand that we already know how to do that, and we're going to go through it briefly. So the easiest one is the aluminum that has an oxidation state of 0 in the reactants. Why? Because the oxidation state of any free element is always going to be 0. So that's the easiest one. And let's go ahead and turn our attention to the nitrogen and the oxygen over here in this nitrite ion. Now, whatever we do for this nitrite ion, you can see that it's actually a very similar formula to this, where we have some element with 2 oxygens and an overall charge of -1. So this is pretty easy. Once we figure out the nitrogen in the nitrite, that's going to be the same as the aluminum in the aluminate ion over here. So if we turn our attention to the nitrite ion over here, there are 2 rules that are going to come into play for assigning the oxidation states. One is that in general, the oxidation state of oxygen, unless otherwise specified, unless there's some other element that has a higher precedence, is going to be -2. So oxidation state of oxygen, this one is -2. That'll usually be the case, and like I said, unless there's some other element that sort of precedes oxygen. There's a table of decreasing preference where fluorine is at the top and then oxygen follows fluorine, and it's always -2. So then the other rule that's going to come into play is that the oxidation states of every atom in this formula, the sum of those oxidation states is going to be equivalent to the charge of the ion, which in this case is -1. So if we set this up like an algebraic equation, we have some number, which I'll call the oxidation state of nitrogen, right, ox sub n, plus twice the oxidation state of oxygen, because there's 2 oxygens, so 2 times the oxidation state of oxygen is equal to -1, the overall charge of this polyatomic ion, right? And so we can substitute in -2 in place of oxidation state of oxygen here. So we know that the oxidation state of nitrogen plus 2 times -2 is equal to -1. Simplifying it down further gives 2 times -2, which is -4. So the oxidation state of nitrogen -4 is equal to -1. And then simply adding 4 to both sides of this equation, we will isolate our variable, our oxidation state of nitrogen, which when we add 4 to both sides of this equation, that's going to be the oxidation state of nitrogen is equal to +3. So we've just figured out the oxidation state of nitrogen. It's +3. And applying the same logic will also give us an oxidation state of +3 to the aluminum in the aluminate ion. The oxidation state of oxygen is also -2, just as it was in the nitrite ion. So if we go now to the ammonia here, we have the nitrogen, we have the hydrogen, and for a similar reason that the oxidation state of oxygen is -2, the oxidation state of hydrogen is +1. It's in that table of decreasing precedence with fluorine at the top and then oxygen and then hydrogen. So given that the oxidation state of hydrogen is +1, we can apply that same rule where the sum of the oxidation states of everything in this is going to be equal to the charge. In this case, we have a neutral NH3 molecule, so the charge is 0. So we have the oxidation state of nitrogen plus 3, because there's 3 hydrogens, times the oxidation state of hydrogen is equal to 0, right? And if we substitute plus 1 in place of the oxidation state of hydrogen, we'll get 3 times plus 1. And then simplifying it down further gives the oxidation state of nitrogen plus 3 is equal to 0. And then subtracting both sides of this equation, subtracting 3 from both sides of this equation gives the oxidation state of nitrogen and ammonia as minus 3. So we have a minus 3 for the oxidation state of nitrogen. So step 1 is complete. We have successfully assigned oxidation states to every element in this equation. We can move on to step 2. Step 2 is to write the half reactions, separate this overall reaction into 2 half reactions, one for oxidation and one for reduction. So I'll just label my oxidation half reaction up here, and then I'll label my reduction, give myself a little bit more room because these things do get quite lengthy sometimes. My reduction half reaction down here, right? And so another part of step 1 that I sort of forgot to do, I mean, we'll have to remember it at some point, is to identify what's being oxidized and what's being reduced, right? So remember, oxidation, that's the loss of electrons. Reduction is the gaining of electrons. So an increasing oxidation number corresponds with oxidation. So of the aluminum, of the nitrogen, which one of those two is increasing in oxidation number? Well, that would be aluminum because it's going from 0 to plus 3. So we know that the aluminum half reaction is going to be the oxidation half reaction. So we have our Al, and then we have our AlO2 over here in the products. Now, for the purposes of clarity and brevity, I'm going to omit the states of matter, the solid for aluminum, the aqueous for the aluminate ion. Whoops, almost forgot to put that minus in there. So let's just imagine that they're there, but I'm not going to write them in just to make things cleaner and faster. For the purposes of redox, they're not super important at this stage. So given that our oxidation half reaction is the one with aluminum and aluminate ion, the reduction half reaction is going to be the other one with the nitrite and the ammonia. So let's go ahead and fill that in. We have NO2 minus, and then over here we have NH3. Okay, so now we've successfully separated this reaction into 2 half reactions, one for oxidation, the other for reduction. Now step 3, it's a pretty big step. There's a lot of little sub-steps involved in step 3. The first sub-step of step 3 is to balance all elements other than hydrogen and oxygen. Now in this case, if we leave all 4 of these coefficients as a 1, this step is already complete. We have 1 aluminum over here, 1 aluminum over there, we have 1 nitrogen over here, we have 1 nitrogen over there. So other than hydrogen and oxygen, these elements are already balanced. So we're good to go for that one, so we can move on. The next one is to balance oxygen by adding water. So in the case of the oxidation half reaction, we have 2 oxygens over here, so we need to add enough water to give us 2 oxygens over here. So how many waters do we need to add to get 2 oxygens on the left? That would be 2, right? Because 2 times the understood coefficient of 1 here for this oxygen is 2 oxygens. So oxygen is now balanced with our oxidation half reaction, and by the same logic we're going to add 2 waters over here, right? We have 2 oxygens over there, we needed 2 oxygens over here, and so we add 2 waters. So the next one is to balance hydrogen by adding H+. So for our oxidation half reaction, we don't have any hydrogens over here on the right, and we have 4 hydrogens, 2 coefficient times 2 the subscript. That's 4 hydrogens on the left, so we're going to add enough H pluses to give us 4 hydrogens. That's going to be 4 H pluses. And then in the case of the reduction half reaction, looks like we have, well, we have to be careful because there's 2 sources of hydrogen here. There's 3 hydrogens in ammonia, and then we have 2 times 2 or 4 hydrogens in the water. So in total we have 3 plus 4 or 7 hydrogen atoms in the products. So we need 7 H pluses. Very important to add all the hydrogen up. Otherwise this thing will not be balanced by the time you're done. And it'll be really frustrating to try to go back and figure out where you went wrong, which is exactly what happened to me when I worked this problem out previously. Everybody makes mistakes, right? Now the next step, and we're still in step 3, but the next, smaller sub-step in step 3 is where doing these things in basic solution starts to differ from acidic solution. So up until now, all the steps have been the same, right? But this step that we're about to do is unique to doing them in basic solution. You won't find this step in acidic solution, and that is to neutralize the H pluses by adding enough hydroxide ions, those are OH minuses, to neutralize each H plus. And we're going to add the same number of hydroxide ions to each side of the equation. So in the case of our oxidation reaction, we're going to add enough hydroxide ions, right, to neutralize all of our H pluses. In this case, that's 4. We need 4 hydroxides to neutralize 4 hydrogen ions, H pluses, right? And then for our reduction half reaction, it's going to be 7. We have 7 H pluses, so we need 7 OH minuses. And don't forget, we need to add the same number of hydroxides to both sides of the equation. So up here we added 4 on the right, so we need to add 4 on the left. And then over here we added 7 on the left, so we need to add 7 on the right. Now, it's important to understand that anytime you have anytime you have an H plus and an OH minus, you can simplify that down by thinking of them coming together to make water. So if we have 4 H pluses and 4 H minuses, 4 OH minuses, we can simply consider that 4 water molecules. So I'm going to simplify that down right here. So 4 H pluses, 4 OH minuses, that's the same thing as 4 waters. And applying the same logic over here, we've got 7 OH minuses, 7 H pluses. That's the same thing as 7 waters, right? So step 3 is finished. Now step 4 is going to be to balance each half reaction with respect to charge by adding electrons. So I like to sort of figure out what the total charge of each side of each half reaction is, and then figure out how many electrons we need to add according to that. So in the case of the oxidation half reaction, what's the total charge on the left and on the right? The oxidation half reaction, well, we have 4 hydroxide ions, each with a charge of -1. So the charge is 4 minus on the left-hand side of the oxidation half reaction. And then there's no charge anywhere else, no charge in the water, no charge in the aluminum. And then on the right, we have a single aluminate ion with a charge of 1 minus, so I'll just write that in, 1 minus, and again, no charge from the water. So the question is, how many electrons do we need to add to the right-hand side of the equation to get the same charge as the left-hand side of this half reaction? That would be 3. If we add 3 electrons with -1 or 1 minus charge apiece to the right, we'll get the same charge on the left, right? So I'll go ahead and add my 3 electrons here. And so now this half reaction is balanced with respect to charge. And then for my reduction half reaction, we take the same approach. Looks like we have a charge of 1 minus for the reactants, because we have a single nitride ion with a minus or a 1 minus charge. And then on the right hand side, we have 7 hydroxide ions, each with the charge of -1. So our charge is 7 minus. So the question again is, how many electrons do we need to add to the left hand side of the equation to get the same charge as the right hand side of the equation? We need a charge of 7 minus. We only have a charge of 1 minus, so that means we need to add 6 electrons, right? Give myself a little bit more room here. So now both half reactions are balanced with respect to charge. So we're moving on to step 5. Now step 5 is to make the number of electrons in both half reactions equal by multiplying one or both of the half reactions by a small whole number, by some factor, right? So as you can see, in the oxidation half reaction, number of electrons is 3. In the reduction half reaction, the number of electrons is 6. So the easy fix for that is to take the entire oxidation half reaction and multiply it by a factor of 2, because 2 times 3 electrons will be 6 electrons, and we can leave the reduction half reaction alone for the time being. So if we're going to multiply this entire half reaction by 2, that means we need to multiply every single coefficient on every single one of these chemical species by that factor of 2. I'll go ahead and take my parentheses and my 2 away and just understand that we're going to be multiplying everything by 2, right? So that 4 for the hydroxides, we're going to multiply that by 2, and that's going to become 8, 8 hydroxides. The 2 waters, multiply that by 2, that's going to become 4 waters. The aluminum, 2 times the understood 1 in front of that aluminum is going to be 2. For the aluminate, 2 times the understood 1 is going to be 2. We had 4 waters over here on the right, so I'll go ahead and simplify that down, or multiply it by 2. That'll become 8 waters. And then 3 electrons times 2, as we said previously, that's 6 electrons. And as I said previously, we're going to leave the reduction half reaction alone, right? So that step's done. The number of electrons for both half reactions are equal. So now we can move on to step 6, which is to simply add the half reactions together, and we're going to be canceling out electrons and canceling out other species as necessary. So it's just like an algebraic equation. Anything that you have on the left-hand side, if there's something identical to it on the right, they're just canceling out, right? So obviously, our 6 electrons are going to cancel for both half reactions. But what else can we cancel? Well, it looks like we have 8 hydroxides over here, 7 hydroxides over here. So all 7 of these hydroxides are going to cancel with 7 of these 8 hydroxides. So that's going to leave us with just 1 hydroxide ion, right? And then if we look at the waters, there's a couple ways to do this, but if you add up the total amount of waters, because we have water on both sides of both reactions, right? So we have 4 waters over here and 8 over there, 7 over here and 2 over there. So if we add the waters together on the left, that's a total of 11 waters, right? 4 plus 7 is 11 waters. I'll just write that in real quick down here. 11 waters. And then on the right hand side, we have 8 plus 2, which is 10 waters. So all of the waters on the right are going to cancel out, leaving us with just 1 water on the left. So basically that just means we'll cancel, 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 and we'll end up with 1 water. Hopefully I didn't do that too fast and lose you. I hope you're still following. I know I did that kind of quickly. So it looks like we've canceled out everything that we're going to cancel out. And so at this point, I think we are ready to just write the equation out as if it's one just one big equation, right? So I think I'll just go ahead and do that in blue, and I'll kind of I don't know, maybe I'll just kind of sandwich it in the middle, and then once I've sandwiched it in the middle, I'll kind of erase everything else. So we have OH minus, right? Try to give myself as much room as possible because these things do get really lengthy. OH minus, and that's aqueous. I'm going to go ahead and put the states of matter back in, plus the 2 aluminum, that's a solid, plus 1 water, that's a liquid, and then we have the nitride ion, NO2 minus, aqueous. So that takes care of everything on the left hand side. So I'll go ahead and just kind of erase everything that was on the left hand side of the half reactions just to clean it up, and then go ahead and put my reaction arrow in there. We have our 2 illuminates, that's 2 AlO2 minuses, aqueous of course, and then we have our ammonia, that's NH3, And then we have, oh, that's it. So that does it for our combined reaction. And I'm going to erase these because we no longer have half reactions. Now we just have a what we think is a balanced combined redox reaction, right? But that that segues us well into step 7, which is to verify that the reaction is balanced. So to do these, I like to sort of set up a little table here where we have reactants, we have products, right? And then, well, that's not a very straight line. Let's try that again. Still not a very straight line, but let's move on. And so we have all these different elements, right? We have oxygen, we have hydrogen, we have aluminum, we have nitrogen, and we have charge, right? Oxygen, hydrogen, aluminum, nitrogen, and charge. So we can go ahead and just add, or add up all the oxygens on each side, make sure they balance all the hydrogens and everything. So starting with oxygen, we have 3 sources of oxygen over here: hydroxide, the water, and the nitrite. So we have 1 oxygen here in the hydroxide, plus 1 oxygen here in the water. So far that's 2. And then 2 oxygens over here in the nitrite. So that's a total of 4 oxygens on the left. Do we have 4 oxygens on the right? Looks like we do. We have 2 aluminates with 2 oxygen apiece. 2 times 2 is 4. So oxygen is balanced. Moving on to hydrogen, we have 1 hydrogen over here plus 2 hydrogens over here. So that's a total of 3 hydrogens. Do we have 3 hydrogens on the right? Yes, we do. We have 1 ammonia, so that's 3 hydrogens. For the aluminum, how many aluminum do we have? Looks like we have 2 aluminum on the left and also 2 aluminum on the right. So far, so good. Aluminum is now balanced also. Nitrogen, looks like we have 1 nitrogen on the left there, and we also have, look at that, we have 1 nitrogen on the right as well. So far, we are looking pretty good here. And then overall, the charge, well, we have 1 hydroxide ion with 1 minus. We have 1 nitrite ion with 1 minus. So the charge on the left-hand side is 2 minus. And then over here, we have 2 of these aluminate ions with 1 minus apiece. So that's 2 minus on the product side of the equation as well. So yay, the equation is balanced. That means we were very good, very careful. We didn't make any mistakes along the way. And it looks like the only mistake that I've made is just not simply putting in the G for gas over here on the ammonia. It's kind of hard to keep up with this. There's a lot of details. I have a hard time with it myself sometimes, although states of matter aren't particularly important for balancing the reaction. All right, so that about wraps it up. I hope this video was helpful. I do appreciate you watching, and I would also appreciate if you wouldn't mind to leave a thumbs up on the video if you think it was well deserved, and don't forget to subscribe to the channel if you're not already subscribed, and click that notification bell, select all notifications so you'll be updated the instant my next educational video is uploaded. All right, thanks again for watching, and next video coming as soon as I can bang it out. All right.